SwayamPrabha. Digital India. Educated India.
Very good afternoon. I welcome you all to the session of thermal engineering basic and applied, and today we shall solve two numerical problems from vapor compression refrigeration cycle. If we recall our discussion that we had in the last class, then we can understand the operational aspects of a vapor compression refrigeration unit. So, in the last class mainly we have discussed about the processes those constitute together to form the vapor compression refrigeration cycle. Then we have also identified the role of several components, I should say mechanical components pertinent to the vapor compression refrigeration cycle, and identifying all those components we had mapped several processes occurring in different components both in TS and pH diagram. So, in the last class just we have mentioned about the refrigerating effect or refrigeration effect, and typically that refrigerating effect is represented by the tons of refrigeration. So, what is the physical significance of this particular unit? Let us discuss here today. So, if we try to recall, tons of refrigeration. So, this is basically the unit of refrigeration effect or refrigerating effect, and whenever we design or a designer designs a refrigerating or refrigeration unit system, typically the most important term that is taken into account is the tons of refrigeration. So, this is basically the capacity of that particular unit, capacity of having refrigerating effect. So, what is the physical meaning of this? This is basically equivalent heat extraction that could change 1 ton of water into 1 ton of ice in 24 hours. So, if we write, so this is basically 1 ton is equivalent. So, it is equivalent heat extraction that could change one ton of water into 1 ton of ice in 24 hours. Typically 1 ton of refrigeration is 3.5 kilowatt. in SI unit or 211 kilojoule per minute. So, this is basically the 1 ton of refrigeration. In other way you also can define it, this is equivalent heat transfer from the it is heat transfer from the surroundings, that is equivalent to convert to melt or convert 1 ton of ice into water in 24 hours. So, this is basically 1 ton of refrigeration. Why it is important? Because in most of the refrigeration units, this unit is typically used to denote the capacity of that particular unit. So, this is 1 ton. Now, if we recall in the last class we have also discussed about the working fluid, and if we try to recall, the working fluid typically used in the refrigeration cycle is basically a refrigerant. So, what kind of property this particular working fluid should have is very important to know. So, today let us discuss a bit more about this particular aspect, that is the properties of the refrigerant. So, I am writing properties of the refrigerant. If we recall the schematic depiction, so this is basically evaporator, and so this is basically refrigerated space. And this heat, this temperature of that particular space is always maintained at a very low limit, that is up to the designer. If you need to maintain temperature of this particular unit, particular space should be at minus 10 degree Celsius. So, this is basically cold space, temperature will remain always minus 10 degree Celsius. So, there must be a continuous heat extraction from the space by the working fluid, and that is that process occurs here in evaporator. So, basically the quality of the refrigerant at the exit of the evaporator is saturated vapor. So, this is saturated state, saturated vapor. If we try to recall that point 1, that is located on the saturated vapor line. Now, we have also discussed that the quality in the point 4 is inside the dome. So, basically the quality of the refrigerant at the inlet of the evaporator, that is mass fraction of vapor in a liquid vapor mixture, that is also known as flash gas fraction. So, this is this is neither purely liquid nor purely vapor. So, it is two phase mixture. Now, question is, upon receiving heat from this refrigerated space, that evaporator will be that refrigerant will be evaporated and essentially will be getting saturated vapor at state 1. So, the question is, temperature you need to maintain always at a sub-zero level for at this space. So, the refrigerant that should be circulated through this evaporator will be able to get evaporate or should get evaporated at a sub-zero temperature. So, that is the most important property, that is number 1, the refrigerant will be capable of getting evaporated at a low temperature and then this low temperature is again subjective, you know what is the temperature, you know. So, if we say this is big, so how big it is, if we say it is low, so how low it is. So, basically sub-zero temperatures. Okay. So, this is number 1. Number 2 is, see, the unit cannot be very, basically that the amount of heat that should be extracted from the refrigerated space, that also will depend on the mass flow rate of the refrigerant. So, and also the latent heat. So, we really cannot increase mass flow rate of the refrigerant for a smaller unit, otherwise the system will be bulky, and also the power input or energy input to run the compressor will be more, because the specific volume will be more. So, the another important quality of the refrigerant is that this particular working fluid should have high latent heat at the sub-zero temperature, so that more amount of heat can be extracted from this refrigerated space. So, this is another quantity, that is latent heat should be high at the sub-zero temperature. So, these two are basically the properties of a refrigerant should have. So, we have understood the physical significance of ton of refrigeration. What is the meaning of this? That means the amount of heat should be extracted by the refrigerant from this refrigerated space or cold space. So, this is also cold space. Okay. And then we have also discussed about the properties that a particular refrigerant should have. So, with this we shall discuss about little bit more about this particular type of working fluid. So, basically these refrigerants are halogenated hydrocarbons and marketed under different proprietary names like freon, genitron, isotone, etc. And the refrigerants are typically either methane based or ethane based. So, refrigerants, they are either methane based or ethane based. As I said you, the refrigerants are halogenated hydrocarbons. So, try to understand and marketed under different proprietary names. So, basically though it is methane based or ethane based, hydrogen atoms should be replaced by several fluorine and chlorine atoms. So, halogens. Now, these methane based refrigerants are basically denoted by 2-digit number. So, this is basically I am writing denoted by 2-digit number, while the ethane based are so a 3-digit number is assigned to the refrigerant which are ethane based. So, now as I said you that refrigerants are given name starts with R, refrigerants are given name and name starts with R. So, it is if it is methane based it is denoted by 2 digit number, if it is ethane based it is denoted by 3 digit number. So, now for the methane based again, so for the methane based you know let us briefly discuss here. The hydrogen atoms should be replaced by halogens, that is fluorine and chlorine atom. So, for the methane based first digit and second digit. So, what is the physical significance of first digit and second digit? So, first digit is basically say R XX, ethane based R Y triple Y, 3 digit number. So, first digit minus 1 is the number of hydrogen atom, second digit indicates number of fluorine atom. So, this is number of fluorine atoms, right. So, this is number of fluorine atom and remaining because carbon methane based. So, this basically you know CH4. So, the first digit is number of hydrogen atom, second digit is number of fluorine atom, you know other atoms are basically chlorine. So, other atoms are chlorine. So, for example, R12. So, this is methane based, we can see because it has 2 digits 1 2 and then basically first digit minus 1, that is number of hydrogen atom. So, first digit is 1. So, number of hydrogen atom equal to 1 minus 1, that equal to 0. Number of fluorine atom is the second digit, that is 2. So, basically you know hydrogen atom there is no 0, fluorine atom 2. So, carbon has 4 valence. So, basically hydrocarbon this you know methane based refrigerant is C hydrogen 0 F2. So, basically there will be another 2 atoms needed to make carbon saturated. So, this is Cl2. So, this is basically R12. So, this is how these refrigerants are you know the name of the refrigerant is given. So, this is basically dichloro-difluoromethane. So, this is dichloro-difluoromethane. Similarly, you also can find out what would be the chemical structure and chemical formula for another methane based refrigerant. Similarly, for the ethane based 3 digit number is assigned to the refrigerant, right. So, first digit is always 1. So, for this first digit is always 1, second digit minus 1 equal to number of hydrogen atom. third digit equal to number of fluorine atom. So, and remaining atoms are chlorine. So, for example, if we take one common example, that is R113 or R134. So, R113, as I said you, it is the name is like this R, then 3 digits Y 113, first digit is always 1, then this is C because ethane based. So, this is C2, right, this is C2 ethane based, first digit is always 1, no issue, second digit minus 1 is number of hydrogen atom. What is second digit? 1. So, 1 minus 1, that is 0, hydrogen atom is 0. So, basically hydrogen atom equal to 0. So, equal to 0, then third digit is number of fluorine atom. So, third digit equal to number of fluorine atom, that is 3. So, C2Cl3, and then remaining basically there are total 8 out of this CCl3. So, basically you can understand, sorry, this should be F3. So, this is F3, this is F3, second digit is 3, third digit is 3. So, that is number of fluorine atom, and other or remaining atoms are chlorine atom. So, C2 there are total 8, C versus C. So, there will be 6 remaining valence. So, basically 3 are fluorine atom and remaining 3 are chlorine atom. So, basically this is the chemical formula of this particular refrigerant which is ethane based. So, I have discussed this aspect because that may help you to understand by how the refrigerants are given chemical name and their chemical structures as well. So, with this let us now solve one problem. So, the first problem is a refrigerator uses R134 as the working fluid and operates on ideal vapor compression refrigeration system. So, basically working fluid is R134A. So, you can understand this is 3 digit number. So, certainly the refrigerant is ethane based. So, operates on ideal vapor compression refrigeration cycle. The evaporator and condenser pressures are 0.1 MPa and 0.8 MPa respectively. The mass flow rate of the refrigerant is 0.8 kg per second. Determine the followings: rate of heat removal from the refrigerated space, input power to the compressor, heat rejection rate in the condenser, the COP. What would be the COP if compared with that of the Carnot refrigerator operating between the temperature limits, that is 30 degree Celsius and minus 10 degree Celsius. So, you can understand minus 10 degree Celsius, that is the temperature of the evaporator, and 30 degree Celsius, that is the at the condenser temperature. So, basically what we need to do? We need to draw the that is very important, pH diagram. As I said you that if you recall, in an ideal vapor compression refrigeration cycle, out of the 4 different processes, 2 processes occur at constant pressure, one process is basically not isenthalpic process, but that is the process for which enthalpy before throttling is equal to enthalpy after throttling. So, out of these 4 processes, we have seen in one process enthalpy before throttling is equal to enthalpy after throttling, and for another 2 processes pressure constant. So, that is why we have tried to draw the pH diagram. So, now as I mentioned that point 1, so basically if we try to draw the schematic of this particular cycle. So, this is condenser, so this is condenser, this is evaporator, extracting heat from this cold space, and that is throttle valve. So, point 1, point 2, point 3, point 4. So, this is the schematic description of this cycle. So, this is point 1, that is on the saturated vapor line, because we have discussed today again that quality of the refrigerant at the exit of the evaporator is saturated. Now, process 1 to 2, for which entropy is constant, assuming that compression process is an reversible adiabatic process. So, this is the point 2, certainly pressure increases from 1 to 2, because that is why compressor is needed, and now 2 to 3, that is again constant pressure condensation. Now, question is, as I said you that it is very difficult to design a condenser which will ensure us to have partial condensation. So, in a condenser it is the refrigerant vapor will be condensed up to the saturated liquid. So, this is point 3, and then from 3 to 4, as I said you, this process is highly irreversible even internally. So, this process is represented by this dotted line, because the process is very fast, and I have discussed very difficult to identify the intermediate states, and hence it is very difficult to know the path by which the process will occur, and state 3 will be changed to state 4. So, this is the pH diagram. Now, from the given data, it is given that the evaporator pressure is the evaporator pressure is 0.1 MPa. So, basically P1 is 0.1 MPa and P2 equal to 0.8 MPa. Okay. So, this is what we can write from the problem statement. Now, question is, if we try to recall in the last class, we also have discussed whether we would like to calculate the power needed to be supplied to the compressor to drive it, or the amount of heat that will be extracted by this evaporated from this cold space, essentially per unit mass flow rate of refrigerant is enthalpy change across those devices. So, across those devices or components, change in enthalpy is a measure of the heat or work interaction. So, now question is, what would be H1? So, we try to understand. H1 is basically Hg at 0.1 MPa, because this is on the saturated vapor line. So, using the property table, so this is basically 231.35 kilojoule per kg. So, this value we are getting using the property table. Okay. So, this is the value we are getting using the property table. Now, H1 is needed to calculate the amount of heat should be extracted, provided you know H4. Now, question is H, and not only that, what about S1? So, S1 equal to Sg at 0.1 megapascal, and that is equal to 0.9395, 0.9395 kilojoule per kg Kelvin. So, these two we can calculate using the property table for this particular refrigerant, that is R134A, and we get it. Why these two are important? Because entropy is also important to calculate, because for this process S equal to constant, entropy equal to constant. Now, if we go to the next slide, then what is basically T sat. So, basically I am writing here that T saturation at 0.1 megapascal, that is minus 26.43 degree Celsius. So, basically this is the saturation temperature corresponding to that pressure for this particular refrigerant. Okay. If we go to the next slide, then what we know, that process 1 to 2 is an isentropic process. That means S2 equal to S1, and that already you have calculated 0.9395 95 kilojoule per kg Kelvin. So, this is kilojoule per kg Kelvin. What is given? P2 is given, that is P2 equal to 0.8 megapascal. So, this is also given in the problem statement. Now, question is, as I said you, we also need to calculate what would be the enthalpy. So, for any problem, even if you recall the problem that we have solved for the steam power plants, essentially we had to calculate enthalpy at each and every state point. Similarly, for this cycle also we need to calculate enthalpy at each and every state point. Note that enthalpy at state point 1 already you have calculated. We are trying to calculate enthalpy at state point 2 by knowing the other two properties, and if we can calculate enthalpy at state point 3, that would be equal to the enthalpy of state point 4, because the process that occurs in this device, that is throttle valve. So, this is throttle valve, right. So, this is throttle valve and this is compressor. So, this is compressor. So, basically we need to calculate enthalpy at state point 2. So, knowing the entropy and pressure, we also can calculate enthalpy from the property table. So, again using the property table, now question is, we will certainly use the property table, but at least we should know where this point should be. Though we can really understand from this pH diagram that point 2 is on the point 2 is outside this dome. So, that is in the superheated regime, but let us verify it. What we can do, we can calculate Sg corresponding to this pressure 0.8 MPa, and that is equal to 0.9066 kilojoule per kg Kelvin. Now, the enthalpy of the refrigerant at the exit of the compressor for this particular problem statement is 0.9395. So, which is, that means S2 is greater than Sg at that pressure, that is the 0.8 MPa. So, this indicates point 2 is in the superheated regime. Now, using the property table, as I said you that you can use the property table for R134A and you can calculate just by linearly or linear interpolation. So, using property table and employing linear interpolation, we can have H2 that equal to 274.47 kilojoule per kg. I would like to tell you one important point. See, certainly we can get it from the property table, there is no doubt about it. Even we can get the value from the property table, but here the pressure that is given 0.8 MPa. It may so happen that we may require to calculate enthalpy at point 2 corresponding to pressure that may not be 0.8 MPa, that may be 0.815, 0.8075 like this. For that, you may not get data tabulated in the table for that particular pressure. In such a case, we need to go for interpolation twice, because in that case neither entropy nor pressure for which we are interested in this enthalpy or we are interested in calculating this enthalpy will not be readily available, because for 0.8 MPa it is readily available, but it may not be available say for example 0.8135. For that it is little tricky that we have to go for linear interpolation twice, because for that we need to take at least 3 different data points for which the linear assumptions, the variation of the linear variation assumptions we can consider and we can calculate by using linear interpolation theory. So, this is H2 for this particular case. Now, if we recall that already we have calculated H1 in the previous slide, that is 231.35 kilojoule per kg. Now, we have calculated H2 again, that is 274.47 kilojoule per kg. Now, what next we have to do? We have to calculate enthalpy at state point 3. If we can calculate enthalpy at state point 3, then we have no need to calculate enthalpy at state point 4, because this is the process for which enthalpy before throttling is equal to enthalpy after throttling. So, H4 should be equal to H3. Now, if we would like to calculate enthalpy, rather we have to calculate enthalpy, then what is the clue? Clue is, the process 2 to 3, that is the condensation process for which heat should be rejected. Now, the process terminates at a saturated liquid line. That means, this is not a partial condensation. So, vapor, superheated refrigerant vapor should be now converted into saturated vapor, saturated liquid, and hence we can calculate enthalpy at state point 3, that is the enthalpy of saturated refrigerant corresponding to the pressure, that is 0.8 MPa. So, basically H3 equal to HF corresponding to that pressure for which the condensation process will occur, and this H3 equal to 93.42 kilojoule per kg. And as I said you that H4 should be equal to H3 and H4 equal to H3, that is enthalpy after throttling is equal to the enthalpy before throttling, and this process 3 to 4 occurs in a throttle valve. Right. So, H4 also 93.42 kilojoule per kg. So, we have now calculated enthalpy at all state points. Next, let us look into the problem statement once more. We have to calculate rate of heat removal from the refrigerated space. So, what would be the rate of heat removal from the refrigerated space? Here mass flow rate of the refrigerant is given, because m dot refrigerant is given, multiplied with the change in enthalpy. So, that is H1 minus H4. So, let us now write it. So, rate of heat removal, rate of heat removal from the evaporator equal to m dot refrigerant into H1 minus H4. Already we have calculated that 0. What is given? Mass flow rate is given 0.8 kg per second. So, this is 0.8 into what is H1 minus H4, H1 equal to 231.35 minus 93.42. So, that should be kilowatt, unit should be kilowatt. Kg per second into kilojoule per kg. So, kilojoule per second, that is kilowatt unit. Similarly, we can calculate input power to the compressor. So, input power to the compressor equal to again m dot r into H2 minus H1. This is H2 minus H1, because again we are applying steady state steady flow equation across all the devices, and that is why we could write this is the heat removal rate, this is the input power to the compressor. So, this is again 0.8 into what is H2 that we have calculated, H2 that is 274.47, 274.47 minus 231.35, again that is also kilowatt, unit is kilowatt. And then next is heat rejection rate, heat rejection rate in the condenser equal to again m dot r into H3 minus H2. So, no, this is H2 minus H3, because enthalpy at state point 2 is higher than enthalpy at state point 4 certainly, that is why we are going to have heat rejection. So, that is again 0.8 into 274 to 74.47 minus H3, that is 93.42 unit is kilowatt. Next is we have to calculate what is COP. So, that is coefficient of performance. For this particular case, for the it is not heat engine. So, this is basically refrigerator. So, for this coefficient of performance is Q in, that is heat removal from the refrigerated space divided by work input to the compressor. In fact, that is this heat removal from the refrigerated space is also known as refrigerating effect. So, this is basically we can write that is m dot r into H1 minus H4 divided by m dot r into H2 minus H1. So, already we have calculated this quantity and the quantity that is equivalent to work input to the compressor. So, this is the COP. Now, question is, the last part of the question is very important, that what would be the COP if compared with that of the Carnot refrigerator operating between 30 degree Celsius and minus 10 degree Celsius temperature. So, try to understand, in the last class also we had tried to discuss that what would be the differences had it been a Carnot cycle. So, instead of a variant of the vapor compression refrigeration cycle, had it been a Carnot cycle, what would have been the differences, and we had discussed. And now question is, if we consider this, then COP basically, so COP that we have calculated, that is for the vapor compression cycle, and COP of the Carnot cycle would be equal to, so this is given minus 10 degree Celsius. So, T1 by so this is T1 divided by T2 minus T1. So, that is minus 10 degree. So, this is 263 divided by T2 minus T1, that is 40. So, if we compare, this would be the COP. Now, you also need to calculate COP of the vapor compression refrigeration system. We also need to calculate COP of the Carnot following this. Now, then you compare what would be the COP of this particular if compared with that of the Carnot engine. So, to summarize today's discussion, we have discussed about the unit of refrigerating effect, then we have discussed about the important properties of a refrigerant should have, then we have also talked about the nomenclature of the refrigerant, and finally, we have solved one example illustrating the concept that we have discussed in the previous class. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.